Hi, my name is Mike Scriber. I am a Senior Director of Server Solution Management, which is a big, long title that I have no idea what that means. But that's the title that they gave me. So I work at Supermicro, and gosh, I'm having a lot of fun there. So I've worked at a lot of other companies that I guess will remain nameless. It's not that I didn't have fun there, but man, Supermicro, we get to do cutting edge stuff. When I worked at another company, I thought, oh, I'm doing cutting edge. I had no idea. I really get to do cutting edge now because you know you're doing cutting edge when you're the only one that has it. Yep, that's cutting edge. So we're going to talk about EDSFF. A lot of you know about this, a lot of you don't, which is what surprised me. I thought about this about 6 months ago. What would I possibly talk about at SDC? And I thought, well, I could talk about EDSFF, but everybody knows that. And then I went to the International Supercompute in Frankfurt, Germany. Everybody I talked to, with maybe I could probably count on one hand how many people knew about EDSFF. Nobody knew. So I think a lot of us developers may know about it, and I've even found, even in this conference, I've said EDSFF to people at our little table, and they go, I don't know what that is. So that's really surprising. So by the end of this, you're going to know what EDSFF is, okay? At least as much of it as I want you to know. There's more to know, but don't think about those things. Just worry about what I'm telling you. How's that? So form factors. We all know and are very, very used to U.2, M.2. Those are very popular. They've been around for a long, long time. Samsung came out with NF1. It's a perfectly great product. I used to work for Samsung, so I have to say good things. It is. It's a fine product, but it is proprietary to Samsung. And Intel came out with a thing that looked a lot like this called the Intel Ruler. That was also proprietary. And I designed a product for the ruler, which allowed me to very, very quickly switch over to EDSFF. Okay, Intel just joined. I can't badmouth anymore. But what Intel decided is they had this ruler form factor, which really was a very, very great design, but they knew that it was proprietary. So I'm pretty sure they instigated it, and John Michael could probably say yes or no, and created a spec that was more common and across the board and open, and that's what we're going to talk about, and that's what EDSFF is all about. Now you'll notice we talk about E1.L and E1.S. There's lots more. There's 3-inch, there's 2-inch, there's short, there's lots of versions of short, there's longs, there's lots of versions of longs. And I heard at the Bird of the Feather last night, a frustration about how many there are, and I'm just as frustrated because I don't want to design a box for every one of those silly different form factors. So the ones we're going to really focus on, E1L, E1S, and we're talking about the high density versions, not the ones that have big fins all over the place and take up space and do that kind of stuff, because there's good reason for that. I just don't know what they are. So why do we need another form factor? Why? I mean, come on, U.2, there's nothing wrong with it, right? Well, I can think of a few things. But one of the things that we really want is we want high density storage. We really, really want to go even more and more dense. A U.2 doesn't fit in a 1U very well. I managed to get 32 of them in a 1U, but this does it a whole lot more efficient. One of the biggest things you're going to see about EDSFF is the thermals, and that's where the efficiency really comes in. Yes, it's the same drive. As a matter of fact, Intel, interestingly enough, called it a P4500 ruler and a P4500 U.2. It had the same controller, the same flash. So from that standpoint, it performed exactly the same way. So it's just a form factor difference. And for all of you software guys out there, and I know this conference has a lot of software people, don't worry. It's just an NVMe drive. It doesn't matter, because you guys you couldn't care less what the form factor is, and rightly so. So it works just fine. It doesn't need some special drivers, special anything. Just use your NVMe and it's fine. So we want to be able, though, to get a lot more density. And we want to be able to do that in a way that doesn't destroy our thermals. So this is one of the great reasons why we need some new form factor. So what Intel did, along with others, 15 companies got together and they said, we're going to make a whole new open spec that everybody can design to. And so those 15 customers got together. They wanted to make a standard. They wanted to optimize things. They wanted to make it efficient, like the things I just got done saying. So they got together and they did that. And they came up with something that hopefully is future-proofed. One of the biggest things that I love about this slide is the fact that it's PCIe Gen 5 ready. Now, I heard that U.2 couldn't do Gen 5, but I also just heard while I was in this conference that, yeah, maybe it can. But the point is we definitely need stuff that'll support Gen 5 because Gen 5 is coming very, very soon. So they have a connector that the BY4, the 8, and the BY16 are very coordinated such that if you have a BY16 connector, you can plug in a BY4 device, or a BY8 connector, you could plug in a BY4 device. They have these numbers, 1, 2, 3. These numbers are really key for one reason, and that's when we abbreviate, and we're tired of saying EDSFF long, we can say E1, a BY4 connector, L, long. So when you hear about E1.L or E1.S, they're always talking about a BY4. If it's a 2, E2.L would be a BY8, and E3 would be the larger one. And this is primarily for like the 3-inch form factor that we're not going to talk about. But it's out there. So here's what it looks like, actually. Because I don't want any of you to steal these off of my table, I took them with me. Here's what they really do look like. It's a cool little design. The great thing about it is, one of the things that Intel did, and I'm hoping other vendors will do likewise, learn from that, is this board down the center that contains all of the flash, the controllers, and everything in it, they thermal greased every component in here to this case. What does that do? That means this case is one monstrous heat sink. Well, actually heat spreader, right? So it spreads the heat across. It does a really, really great job thermally for that. The other thing you'll notice about it is the height is magically, amazingly, very, very good for a 1U per design, right? So this fits very nicely in a 1U, and the spacing of it makes it so that I can put 32 of these very easily into a 1U box. And that was the idea. How can we get 1U to have a petabyte of flash? And that was kind of the promise we've had with these things from the very beginning, is a petabyte of flash in a 1U. And you'll see on my slide, actually I reviewed my slides in the last session, right? I decided maybe I should look over my slides and realized I had a date in there for the 32 terabyte drive. I changed the date because Intel did. And you'll see that, and we'll laugh at that in just a little while. So, there's some good reasons why you would want this. Here is the best reason. If you guys don't remember anything else about this whole talk, remember this slide and the next one that's about to come. Because what I would say is the biggest reason why EDSFF will take over the world, and that's what I tell everybody, it's going to take over the world. And the biggest reason is this. When I design a backplane for U.2, what it does is it's a huge air dam. It sits right in front of this box. It's great, plug it in, it works fine, except it's a huge air dam. It blocks all my airflow. Now, what are all the hot things in this device? They're all back here. It's the processors, it's the memory, it's my PCIe cards, it's my power supply that needs good airflow. All of this needs good airflow. What's keeping it from having it? This stupid backplane. It gets in the way. Now, if you've ever designed a backplane, here's what you do. You design your backplane, you put your connector in, you route it, and you punch as many holes in there as you possibly can because you're trying to get some airflow to go back into the rest of the box, right? It's a pain. Here's what EDSFF very intelligently did. They took that backplane and they laid it down flat. Now there's nothing blocking the airflow. And you're like, well, how can you connect to it? What they did is they used these vertical connectors, right-angle connectors, that sit right on a very flat backplane. If you even want to call it a backplane, it kind of still is. And it's no wider than the device itself. So if you ever look, and you can, because you can go to our table and you can peek in the thing, and you'll see the connector fits exactly right, the same width as this device. What does that mean? It means there's nothing blocking the airflow. Hooray! This is why the thermals are so much better with EDSFF, is now I can design this and have all of my air go right through the device and get back to those processors and memory and all of those hot things. And as long as we make fun of Intel, and they keep getting hotter, right? And you'll notice that as you see specs, because it just keeps getting higher TDPs. So that's probably one of the greatest reasons why EDSFF is so wonderful. How does that help me? What that means is my airflow can now reduce by 55%. Yes, this is an Intel slide, so don't believe those numbers. Did you? I thought you might. That's why I'm little fun. No, but this is where the thermals become so much better. And because of that, what that means, I can slow down my fan. What does that mean? I don't have to use as much power because those fans take power. And they especially take power as they run faster. It's not linear. They take a lot more power as they run faster. So if I can slow that fan down, now I can save you power. Now the total cost of ownership seriously reduces because I don't have to use that much power on my thermals. Or maybe I don't need to have some huge air conditioning system to cool this thing because I've got so much better thermals. And so that's something that's really, really critical and something you really, really gain with EDSFF. Very, very smart thing. Like I said, if there's nothing else, people will say, oh, well, we'll just go to U.3. If U.3 still has that silly backplane that's going to block all my airflow, I hate it. That's what I love about this. And wouldn't you know, my phone's going off. Seriously? Shut up. I knew it would happen. It's probably an Intel person mad at me. Just kidding. We'll have fun with Intel. So this is another slide that I'll bet John Michael did. What are some of the benefits? The density gets better, and that's a true statement when you're comparing a 2U24 drive, which is what everybody has, right? Not everybody has a 1U32 U.2 system like we do, but if you compare it to the 2U24, 2.5 times better density, it's hot pluggable. Super important, especially if you want to compare it to an M.2. It's got to be hot pluggable so that you can pull the device out and use it that way. The airflow efficiency, the capabilities of it, all of that cool stuff of why it is so much better. The other thing that Intel did, and I talk about Intel because I'll tell you, Intel's the first one that's come out with an EDSFF drive, so I'm going to talk about them a lot. They're not alone. There are others that are going to come out with them, but just not yet. But one of the things that they did is they also, with the EDSFF drive, it's the first drive that they came out with QLC. Now they also have a U.2, but they came out with it afterwards by about a day or something. Not long, but so I also wanted to talk about QLC. One of the things that I remember hearing by going to Flash Memory Summit year after year after year, the big message that I kept hearing is, boy, when we get QLC, we're finally going to be able to compete against a hard drive. Because why don't we do solid state drives? Oh, they're too expensive. They're so expensive. Well, the price of solid state drives has really gone down, but QLC really gets us into a new realm. Why is that? Well, that's because instead of having 3 bits with TLC, 3 bits per cell, now I can get 4 bits per cell. And that means that I've got 33% more capacity. If I have 33% more capacity, what am I going to do? Of course, I can drive the cost down. Please, Intel. So I can save and reduce the cost by, say, 32%. I did some math on our own. That's actually the number I got. I'm sure Intel doesn't want me to say that because your price may vary, of course. But the idea is we can finally start closing that gap between solid state drives and hard drives. So one of the things I also did is I said, okay, I want to take the price of this drive and I'm going to take the price of a similarly sized 15K spinning drive. 15K was more expensive. 10K, just about the same price-ish. Obviously a 5.4, not as cheap as that. But the point is we're finally getting to the point where hard drives are being more expensive than a solid state drive. Woohoo! So that's great. So now we can finally get to that point. Some key things about this drive, though, because it's QLC, 16K block writes. Don't forget that. Now this is where you software guys can wake up because it's like, what? 16K block writes? Yes, we want to do 16K block writes with this device. We currently have a 15.36 terabyte drive, and there's this promise for a 30.72 terabyte someday. This is where I just modified the slide because I realized I had a date in there that I was just informed is no longer accurate. So Someday, and I've been promised for what, 2 years now, that I'll get one. Someday we will. And when that happens, I will rejoice because then I can finally say, yes, see, I told you get a petabyte in a 1U, and you really can't. The other thing that's coming out is TLC. So TLC EDSFF drives are also coming out, and we're going to have those very, very soon here. I'm still waiting for I think it's shipped from China, is right at the moment. So endurance, the endurance is different. Now you're going to see a bunch of different endurance numbers. There's one number that's kind of an average number because depending on whether you're doing sequential or whether you're doing random writes, it'll be a difference. This is kind of an average number of 0.5. But one of the key things that I find interesting, especially customers, you guys are smart, you figured this out, but customers get really, they're like, oh, if the endurance is like half of my one drive write per day, oh, that's going to be bad. Wait a minute, it's a 16 terabyte drive. So if I'm used to one drive write per day on an 8 terabyte drive, well, that means I can write 8 terabytes per day to this drive. But if I've got a 16 terabyte drive and it's only a half a drive write per day, what do you know? It's still 8 terabytes per day. So you really haven't lost anything. Drive writes per day is important, but it's only important in comparison to what the capacity is too. You've got to add that to the equation because what the customer really cares about is how much data can I write to this drive every day. So as they get larger and larger and larger, the drive writes per day becomes less and less important as an individual number. Take that into context, okay? So this is a specific drive. This is definitely my promotion of Intel drives because I'm going to give you the key spec. But given that nobody else has a drive out there, sure, why not promote Intel's drives? An interesting thing that you're all going to say, yeah, we know that. If you look at IOPS per terabyte, this is awesome, right? I mean, you compare a hard drive, which now is almost the same price compared to, you know, what the IOPS per terabyte is for this drive. I mean, it's 3 magnitudes better. So that's super important. You'll notice over here that endurance number, like I said, it varies. You know, it can be as small, don't trip, as 0.18 or 0.9, depending on whether you're doing random or whether you're doing sequential. But the other important thing to note, some people have wondered about QLC. Well, what about if I just leave that drive sitting, not plugged in, how long will that data stay? Just as long as a TLC drive. There's no difference there. So you don't need to worry about that either. And that has to do with the data integrity for the drive. So you can also see some of the performance numbers. 3200, that's a pretty sweet number for sequential read. But notice the write. The write is half of that. This is key with QLC. QLC is really intended as a read-intensive drive, not really a write-intensive drive. So if you have write-intensive applications, we really recommend you go with the TLC one that's just about to come out. But if you have read-intensive, then the QLC is a great solution for that because I can write to it and then read extremely fast and get great performance on my read. Yes?
The endurance for random versus sequential really is, it's really block size more than access pattern, right? Because if you're doing larger than 16K, the endurance impact, or the effective DWPD will be higher.
Correct.
It'll be closer to that sequential.
Right. Yeah. Yes, you're right. And that likewise, though, if you don't do 16K block writes, you can seriously impact your endurance. Because then what happens, let me just explain this, you end up doing a read modify write. What's going to happen is it's still going to do 16K block. So it's going to read that 16K block. It'll, let's say you're doing a 4K write. It'll plug in that 4K and do a read modify and then write it again. So that really, not only does it mean that if I do that 4 times to do 16K, that hits my endurance 4 times, it also hits your performance, right? Because you're doing this read modify write slowness. So just don't go there. Do 16K, okay? So,
But if you're doing 16K, it still measures big time if it's random or sequential.
yes. Yeah, I think it does impact it. Yes, it does. But depending on how you do it, it could have a bigger picture. So now let's talk about Supermicro. So what have we done? We've created some devices, obviously some systems. Fortunately, I can say you can see these, right? You were out at our table. We have this one in particular. And like I said, originally, way back, I designed a 1U32 drive system that was U.2, modified that, planned to go with the Intel ruler drive, and then I think it was like June of 2018, Intel came to us and said, hey, we'd really like to show a petabyte in a 1U at Flash Memory Summit for 2018. I'm like, that's like 2 months away. Are you kidding? And they're like, no, you can do that, right? And so we pulled it off. It was great. The great reason why we could do that is because it really was just a connector change. We modified the connector that was on that backplane, or what we call a switchboard. We modified that connector from the Intel proprietary version to EDSFF, and it came up, it ran, and it's been awesome ever since. So we ran that for like 3 days straight at Flash Memory Summit. Everybody was looking at it thinking, great, it works, it's great. I'm sitting there going, wow, 3 days, that's really good, because we'd never powered this up before. So it was pretty awesome. I was pretty stoked. And we ran FIO, which is a nice little stress program for 3 days, and it worked great. So we've got this system. It's actually very mature from the standpoint of our motherboard is the same motherboards that we've had actually for a while. It supports Cascade Lake. We managed to fit in all 32 DIMMs, so you can load it up with memory, and it also supports Apache Pass, so you can do that, though I'm sure I'm not supposed to use that word. I'm supposed to use DCPMM, yeah, that thing. Apache Pass, so much easier to say. We also put two M.2s in there as a boot device that we put very nicely in the center of our drive, of our motherboard, I should say, so that you get great cooling there, which you want to do with an M.2 because M.2s don't cool very well. And we also put 2x16 slots in the back so you can get 200 gigabits of Ethernet or InfiniBand or whatever you need for an I.O. out the back. So really loaded it up. One more thing we did is QAT. So most of you probably know what QAT is, but for those that don't, that's encryption and compression that's embedded in hardware. And we wired that up. Not too many people do that, but we thought for this storage device, it would be great because if I've got a petabyte someday, a petabyte in a 1U, if I can encrypt that, if I can compress that data, that could be like 3 petabytes, depending on my compression ratio and blah, blah, blah. So a really, really cool product. Love this product. Likewise, when I designed the U.2 version of I actually first made a JBOF out of it. And so I can take that exact same board that I used in the server, put it in my JBOF, and now I've got a JBOF of this. So what's the difference between a server and a JBOF? Well, one of the big things is it doesn't have any processors or any memory. So the expense of the processor and memory is gone. The JBOF stands for just a bunch of flash, and I can directly connect that with PCIe. So in this system, I've got 64 lanes of PCIe coming out of the box, and I can connect up to 8 host servers to that JBOF so that I can distribute all of that great capability of the drives to multiple hosts. I've heard lots of people say, why would I need 32 drives? I couldn't possibly, there's not enough cores to really support 32 drives if you're doing compute. Well, now you can distribute those 32 drives out to 8 servers if you want. Though most people use either 4 or 2. You can do that too, and distribute that out and have enormous amount of bandwidth into this box. We've measured 52 gigabytes per second of bandwidth in and out of the box, which is pretty much just the limitation of PCIe. What else can I say awesome about this? Other than I love it, it's my baby. Yeah, that's enough. We can individually, it's got all of the enterprise features. It's got all of the server management features. I can individually control every drive. I can do all of those kind of things. And it's awesome. So the other thing that we haven't talked yet about, primarily we've been focusing on the long, but there's also a short. And what are the advantages of the short? Well, especially compared to M.2, which is just about the same size. It's a little bit taller because that allowed more space to put more flash, and it still fits nicely in a 1U form factor. But The big difference between that and an M.2 is EDSFF is hot pluggable, whereas an M.2 is not. So that's a big deal. So you get all of the great density benefits, you get all of the hot pluggability, all of the great cooling benefits, all of those things just kind of go with EDSFF. But the big advantage versus M.2 is that hot pluggability, really, is the huge difference. So of course we have a server, and we have the PM in here that's doing that in the audience. He should come up and talk now. So this is our short version. Don't tell Intel. That's supposed to be funny. They're in the room. We took our NF1 server that we made for Samsung, and we took this same box, same motherboard, same everything, and just converted it into EDSFF short. So that's where that came from. 32 drives. There's now, the original spec really only had what we now call the 5.9 millimeter board. So that's what we designed it to. Since then, we have, I think, a 9.5 version, a 25 millimeter wide version. There's 1,000 different versions of short, but this is designed primarily for the 5.9 millimeter, but I think the 9.5 would also work. With the case, it would also work, assuming that we've got the latches working there. This has got a similar kind of motherboard. It's not the exact same one, but 24 drives, 2x16 slots, and an extra by 4 slot. Is that right? Yes. Yeah, extra by 4 that's back in here, and supports the Cascade Lake processors and all of that. The really cool thing about this is this will also support 205 watt procs, whereas I can't do that with the other box because it's so long. It's 36 inches long. I had to cram a lot of the components up against the power supplies, and that kind of limited how much I can do in the power for the processors. So we're going to fix that next go-around on the next revision of Intel processors, which we're working on right now. It also has the QAT in it, so a really, really great box, really awesome system that is coming out soon, just as soon as Intel releases their short version. We will be timed to market with them. And last but not least, we're also creating this. We have an awesome product called Big Twin. I don't know if you've ever seen Big Twin. Big Twin rocks. Here's the reason why. We make our own power supplies. So I think I've got some time. We'll talk about this. You see this power supply? That's actually a power supply back there. Redundant power supplies, but what you may notice is the width of the power supply is just about the size of the connector for the plug. It's that tiny. So instead of having a normal wide power supply, we made this thing called a power stick. It runs the entire length of the chassis, okay? Big and long, 2,300 watts of power, though, this tiny little power stick can do. And you're like, well, why is that exciting? It's exciting because if I shrink this, it means I can grow that. Normally, when you're talking about a twin system, meaning side by side, you obviously have to sacrifice something. You can't fit as many DIMMs, you can't fit as many stuff, you only have half the space, right? So you obviously have to make sacrifices. The great thing about Big Twin is it doesn't make any sacrifices. Because I can grow that, we're able to fit 24 DIMMs, 2 sockets, 3x16 slots out the back, which is as many as you're going to get on any 1U system. So you take what would be a full 1U system, cut it in half, and still fit all of the features and functions in it. So that's what makes this thing so great, because it's a 2U box that has 4 nodes already embedded in it. So the density of this box is wonderful. Normally what we do is we do like most people. We put 24 drives in the front of a 2U, U.2. But now what we've done with EDSFF short is we are able to put 40 of the drives in the front. So instead of having 6 drives per node, we have 10 EDSFF drives per node. And if you notice, we have a couple little drives that look a little funny over here. Those are M.2s. And we've designed a carrier such that we can hot plug the M.2. So you've got 10 EDSFF plus 2 boot devices out the front for M.2 for each node. The software-defined storage people love this box. They use it a lot. If you ever go to Accelero, AX10, WIC-IO, they all love this box because it's a very dense, awesome solution for them. But the minute you start going to 10 drives per node, they're like elated. It's like, yes, that's finally the number I've been looking for. So this is an awesome system that takes advantage of the EDSFF short and also has the ability to have a hot pluggable M.2. And likewise, it has 24 DIMMs, all of the things that you would want in a full 1U system, and 3x16 PCI slots out the back. It's actually 2 PCI slots in what we call an SIOM, which gives you your network capability with all kinds of different options there. So this is a phenomenally awesome system, and it's probably one of our best sellers that we have. So I did a lot of talking. I have no idea what time it is. What time is it? Anybody? 2:32. Oh, good. We got plenty of time. So the last time I had to get this thing, they said, okay, you've got 5 minutes. So I've probably gone kind of fast. What questions do you have?
Mike, if Intel were to come out with a CPU that had, say, 3 or 4 times as many PCI lines out of the processor, you would be interested in that. I would think that would be epic.
I will avoid the pun. Yes, the more PCI lanes, the better. Absolutely. I'm sorry. Hard to repeat that question because he did it in such an epic way. So he asked the question that if Intel came out with more PCI lanes, would that be an epic thing? And to use his words, there was obviously a pun there for anybody that knows AMD processors. And so yes, more PCI lanes, the better, and that would be awesome.
What do you see as the market size between E1.S versus E1.L? Is C1 sort of being a larger market, or are they going to be about equal? What do you think?
Yeah. Whenever anybody starts with market, I always tune out because I'm an engineer. I like to design stuff. I don't think about markets. But it is an interesting question. So let me answer it the best I can answer from an engineering perspective. I can understand why the short, because the short is almost the same depth as a U.2, and because our industry doesn't change, it's so funny. We're cutting edge, but we take forever to embrace new technology, forever. I mean, think about the transition from 1 gig to 10 gig Ethernet. Took years. So at any rate, but because that's almost the same dimension, I could see where short is easier to design in because it fits in that same space that you always had your U.2. So if that's what you're used to and you don't want to do much engineering, then that's an easy thing to do. So I could see people embracing that. That's not addressing the customer, right? Because the customer is really what you're asking is, what's the customer going to want? It really boils down to, and what Intel has done, John Michael can correct me, is they've really tried to bifurcate the long and the short based on capacity. So anybody that wants the serious capacity, if you're talking 15 terabytes, 30 terabytes, you've got to go long. And they've made the short much smaller. So you've announced the capacity of the short, haven't you? Okay, so 4 terabytes is what the short is. I don't want to say anything that I shouldn't. But 4 terabytes, so there's a factor of 4 difference between those two. So for those customers that don't need 15 terabytes, yeah, they can go with the short a whole lot easier. And certainly in this one, you're getting 10 drives per node. 10 drives per node is nothing unusual. Most 1U 10 drive, no big deal, right? So from a density standpoint, it's about the same. The difference here is it's the first time we've ever been able to do that in a 2U dense kind of form factor. So from that standpoint, I could understand where short could be an advantage. Anybody that wants to design in a long, go look at the chassis. It's 36 inches, and I couldn't possibly shrink it any less. So it has a lot of depth. And there are some customers that are going to say that's just too deep for my rack. So I can't support that. And we've ran into a few like that. Then again, we know other customers are like, are you kidding? I can fit larger than that. It's like, knock yourself out, So that's where it's going to be a capacity play and a depth play. And ease of design in. right? If it's too hard to design in, some people just won't do it. Other questions? Yes?
On slide 7, you said something about, you didn't say this, it was on the slide.
Then it wasn't true. No, I'm kidding. Sorry, that's what Chris said, right?
What was it? Geographic drive mapping. I thought that was pretty cool. On the
Geographic drive mapping for simplified drive management.
Yeah, that sounded pretty cool.
That does sound cool. Did you make this one? You didn't make that slide? Geographic drive mapping.
It caught my eye.
Wow, I wonder if we can come up with other management terms we could throw in here. Geographic drive mapping for simplified drive management. Absolutely. And that's my final answer. Now, certainly, so let me try to dig my way out of this one. You can see I stole this slide, but I liked what it showed. It gives the message I liked, which is why, but yeah, I never noticed that. There are different sections that are going to go to different CPUs. So the location of where you place your drive is going to make a difference on which CPU it's going to go to. So you can control that geographically. There's my answer. Any other question? Yes?
It's not on your slides, but you mentioned that E1.S has like multiple different versions. So you're focusing on one version of it. Maybe a little bit what are the other versions?
There is, the one that I've seen most prominent at Flash Memory Summit, last month or August, is a 25 millimeter wide one where they basically take the 9.5, well, I got it here. Pretend like this is short. They take this 9.5 millimeter version and stick a freaking huge heatsink on the edge, just on one end, so it's not even symmetric, which could be actually kind of okay. There's an 18 millimeter version of this where they have fins on both sides, and of course the problem is the minute you design it for a 9.5 like this is, and like the system you see out there, you can put an 18 millimeter in the middle, but the minute you go up against a wall, well, it doesn't fit, right? So you end up wasting a lot of space. You have to redesign the whole system to shift everything in order to fit an 18 millimeter drive kind of thing. So that's a variant of this, but there's the 25 millimeter, basically huge heat sink that sticks out here. And you may say, well, why did they do that? This is the other thing about EDSFF that I think is fantastic and why it's going to take over the world. We think of it in terms of a storage device. 4 PCI lanes. Let me back up a few slides and it'll be easier to.
Short answer is by 8 to 25 watts is what the new E1.S spec allows.
Yeah. So I was going to get to that, but I was going to get to that in a different way, which is to say, if I've got by 16, do I really need a by 16 connector for storage? I don't think so. So what were they thinking? Well, they're thinking beyond storage. Is there any reason why I can't use this connector or this kind of device and put an FPGA on it? Or this size of a device and put network on it? So now the paradigm kind of shifts. If I've got all this PCIe that's sitting at the front of my box, I can plug in drives. Great, that's what I'm used to on the front of my box, but there's nothing stopping me from plugging in, if someone makes it, a network device, an FPGA device, a GPU device. GPU could be hard to cool, but it doesn't, you've got the PCIe connector there. So especially when you're starting to talk about this by 16 in obviously a 2U form factor, not a 1U, it wouldn't fit, but I can plug in the 3-inch drive, which is what the spec says. I can plug in a bunch of those, but I could also plug in network cards. I could plug in all kinds of different things. It's PCIe. So because of that, they've also come up with a spec. If I wanted to put an FPGA in this device, it would probably use more than the 25 watts that this is spec'd for. So they said, great, 18 millimeters 40 watts. So they were thinking through on, hey, what if we wanted to do other things? And so for that 25 millimeter wide, it has a much higher spec for power so that you could do things like FPGAs or accelerators or ASICs or other things. And I think that's the reason why that they did that. Next question. We have about 8 more minutes to tap dance. Go ahead.
Mention something about segregated storage. Can you talk about it?
Sure. And especially, I think, with the JBOF, you get your disaggregated storage for sure. JBOF is awesome for that. Because what I can do is I can plug these drives into my JBOF, and I can totally disaggregate that. I can use rack scale design to create NVMe pools. You can do all kinds of things to disaggregate your storage with a JBOF in particular. And so that's the best and most awesome example of that is your JBOF, where I can stack on more JBOFs without having to add more CPUs, memory, and all of that other stuff. You were going to ask?
How hot do the dies actually get inside of your system? How hot do they run?
I don't know that we've necessarily specifically measured the die inside, because what we're trying to do is make sure that this whole device keeps cooled, right? And so that's what we make sure. The other great thing is because it's the very, very front of the box, it gets ambient air, right? So it's similar to when we design a GPU system, what we like to do, put the GPUs right up front, you know? That's what we call a GPU system. People that take a 2U standard box and say, yeah, I can plug in GPUs in the back of my PCI slots in the GPU system. It's like, that's not a GPU system. That's just you taking a generic server and slapping GPUs in it. To really design something well, you want to think about the thermals. So that's what's nice about this. You put this right up front, and so cooling of this has never been an issue. Which is why, probably shouldn't say this, but why that certain company insists on having an 18 millimeter fins when it's at the very, very front and it's freaking cold already. I don't get it. It just wipes out the density. But I guess it keeps it so cold that maybe they don't need to worry about other cooling issues. So I guess there's a benefit there, but it's weird. Other questions? Yes?
Dual port and EDSFF?
It can happen. Nothing's stopping it.
Anyone make it? Or is it just
No, not yet. Not yet that I know of.
There's the dual port enablement, similar to that too.
Yep, it's there. It's capable to do it, but we haven't seen a dual port drive from anybody yet. Will it happen? Yes. Because like I said, EDSFF will take over the world. I mean, eventually we'll laugh about U.2 like we laugh about floppy drives. But it will take a long time, right? Because our industry doesn't move fast. So it'll probably take 20 years before we finally get rid of U.2 drives still trying to run it Gen 4. Yes?
What's the cost delta between EDSFF and U2 today?
None. The impact, the cost of a drive is the flash and the controller. So if you change the form factor, it might be minuscule. I mean, I haven't sat down and actually mapped it out on a day-by-day basis to see how the price has changed, but they're pretty much the same. You're not paying a premium for this, right?
Yeah, and the Intel QLC EDSFF is actually cheaper than our SATA.
There you go.
NVMe QLC is cheaper than SATA.
But if he compares it to the NVMe U.2 drive, it's about the same price. Same price. Yeah. There's no extra cost. It's cooler, but we don't charge more. Anything? You mean with that other processor, which would be a great design? Funny, you're not the first person to ask me that. No, we have not made that. But yeah, it's an obvious yes, but no. Any other questions? We got 5 minutes to still tap dance. Yes?
You said about the octane. How do you create that with the TCO when nobody's going to go with a higher capacity on the octane? And you have to still put smaller capacity
So I didn't say Optane, I said Apache Pass, and I'm going to be very specific there, only because what I was talking about is the memory, right? So that system will support the DCPMM memory that goes not. Now, is Intel going to make an Optane drive like this? Well, there's a guy in the back of the room that knows the answer to that. It hasn't come out yet. Are they ever going to do it? I think so. Hope so, right? But as far as using Apache Pass with this, I think actually is a brilliant idea. And the reason why I say that is you say, well, the write speed on this is kind of slow relative to TLC. What if I had Apache Pass DIMMs and I use that as a write cache, and then I could just send stuff out to this drive, as I want, as I have time, in nice big long chunks, so I can get the sequential write speeds, right? So that's where I see Apache Pass working very, very well in the system as a write buffer that's non-volatile, so you don't have to worry about losing your data if you lose power, and can work in conjunction with this.
Could you use memory semantics on Apache Pass, or is Apache Pass strictly for block access?
Oh no, you can absolutely use memory.
So
Yeah.
with the same hardware deployment, you could, for different applications, bunch it all into memory, so you have the DRAM as the cache for those other slightly slower DIMMs, like they've been talking about.
Yes, you could do that too.
The same hardware deployment?
Yeah, there are 3 different modes for Apache Pass. It's not really the topic to discuss here, but there's 3 different modes for Apache Pass DIMMs. And I keep saying that because it's easier to say. DCPMM is the official word. Yeah, the different modes allow you to either do a block or allow you to do just byte writes and treat it just like memory. Yeah, so, and I'm sure there's an entire thing on persistent memory, entire section here where they can go into great detail on that. Anything else? All right, thank you so much. Appreciate your time.